Hello everyone, my name is Aryan Raj, and along with my teammates Tridib and Parth, I am here to present our project titled Tiny Object Aware Multi-Stage Blockwise Framework for Thermal Object Detection using EfficientDet. So here is a quick outline of our presentation. We will begin with an introduction and motivation behind our work, followed by a related research, data sets, our methodology, what we have done enhancement for tiny object and occlusion handling, which we will discuss later on, and finally a discussion on results and future scopes. So thermal imaging play a critical role in low visibility scenarios like nighttime, autonomous driving, or drone monitoring. However, there is a traditional RGB-based method, which which is not as much good as our thermal detection because of the low resolution and lack of texture or color. So our proposed framework addresses the gap by focusing on tiny and occluded thermal objects optimized for real-time deployment. However, making this has some motivations and challenges. So first was the safety critical environment because it requires a reliable object detection. We have to be 100% sure whether the object detection is correct or not. However, the data set which we have used, uh, they are small and noisy, and there is class imbalance which affect the model performance. Also, detecting tiny objects and handling occlusion is difficult due to the low signal to noise ratio, the famous SNR ratio. We have studied many works related to it. Some were the traditional method, where we have used the saliency-based thresholding, where it was a lightweight model, but the problem was it was not good with occlusion detection. Another paper which we have read was the deep learning, which was the YOLO. It it was good for both lightweight also and handling occlusion, but it has a poor generalization. The base paper from which we have made our model is the third one, EfficientDet plus PMBW, that is based multi-block wise detection. It adapted EfficientDet. It was good for medium and large objects, but failed on tiny and occluded ones, which we will discuss how we solve that problem. Another famous one is the RGB fusion, which generally use the RGB colors plus thermal features. It has a high accuracy, but the cost to implement it is very high. So for the dataset that we have used the famous FLIR thermal dataset. It contains training 10,000 training images and approx of 1,200 test images. All the images were of resolution 640 into 512. There were 15 object classes. Some of them were person, car, bike, uh, strollers, skaters, and that all. It was fully thermal dataset, which included roads, uh, day condition, night condition, occluded, tiny objects, all types of problems that we have solved. Also for the annotation, we have used the Coco style bounding boxes. And there were total approx 4 lakh total annotations. So the next the methodology part, which my teammate will explain. But before that, there is a pre-processing part where we have used the pixel before applying our model in the stage method. We have also used some pre-processing. In the pre-processing, it includes pixel normalization, contrast enhancement like adaptive histogram equalization, gamma correction, and data augmentation. For the details of each, we have taken the mean and standard deviation, which we have included in our presentation. So we have to do all this pre-processing before training our model so that we could get the efficient results. The next methodology, which my teammate will explain you.
Hello everyone. Today I'll be presenting our proposed methodology for object detection in thermal images. Our approach is a modular multi-stage pipeline specifically optimized to detect tiny and partially occluded objects with high efficiency and high accuracy. So our detection pipeline has 4 major stages. First one is a lightweight filtering, which is to remove the background blocks. Second is the EfficientDet backbone, which is used for the feature extraction with BiFPN. Third one is the classification and regression, which is used to predict the class and bounding box. The fourth one is the post-processing, which is used for spatial consistency and the final refinement. Now, why the multi-stage? Now, each stage is designed to refine detections and progressively while keeping computational overhead low. Now, in multi-stage detection, we have used efficient use of compute, better small object focus, and early rejection of useless regions. This is our diagram for the neural network. The stage 1, that is a lightweight filtering. Thermal images usually contain large areas like roads or skies that are irrelevant for detection. We address this by applying a shallow CNN model that filters out non-informative 64 cross 64 blocks, which is based on the confidence scores. Only the blocks which are scoring above 0.3 are forwarded to the next stage. This filtering stage alone reduces memory usage significantly while maintaining over 90% precision on the FLIR FLIR dataset. The stage 2 is the feature extraction with EfficientDet. Next, we use EfficientDet of variants D0 to D3 for feature extraction. It uses a bidirectional feature pyramid network to fuse the multiscale features and better detect both small and large objects. The input images are either 768 cross 640 pixels for D3 variants or 512 cross 384 pixels for D0 variants to preserve the fine details necessary for small object and occluded object detection. The stage 3 is for the classification and regression. This stage has two heads, the classification head and the regression head. The classification head predicts class probabilities for each anchor, while the regression head outputs bounding box offsets which are then transformed into actual coordinates. To address class imbalance, we apply focal loss for classification and smooth L1 regression loss for regression. This is our basic block diagram for all the four stages. As you can see, the thermal input image is given, which is initially pre-processed by normalizing and contrast enhancement. The stage 1 is the lightweight filtering model. That goes to stage 2 with EfficientDet feature extraction. That goes to stage 3, which is the classification, regression, and bounding box refinement. Now, we're into our final stages, that is the loss functions. Now, our loss functions, our combined detection loss is lambda CLS plus lambda regression. This balances the precision and localization. Stage 4 is the post-processing, where we're actually showing our contributions. Detecting tiny objects in thermal images is challenging. We apply several enhancements. High-resolution inputs, all the images are upscaled to 768 x 640. Adaptive anchor boxes, generated using k-means clustering on ground truth sizes down to 8 x 8 pixels. Context-aware detection, contextual attention layers are added to bidirectional feature pyramidal network. Selective enhancement of blurry regions using ESRGN and SRCNA. These enhancements together boost our mean accurate precision from 70.4% to 77.3% on the FLIR dataset. The third one is the occlusion handling. Thermal images often partially contain occluded objects. To address this, we introduce multi-stage refinement where low-confidence early detections are revisited with deeper layers. Our model performs well on occluded targets with a MAP or mean average precision of 55.4% compared to the 89.2% for fully visible ones. Now, my teammate Aryan Raj is going to show the live demo for our model using one of the images of FLIR dataset.
So this is our implementation for the whole model, which Tridib has explained about you the model. So this is, you can see here, there are 4 folders: pre-processing, where it is the contrast enhancement, flipping, normalizations. It's 4 stages as they shown. The lightweight model is implemented here. Stage 2, where EfficientDet and extracting features were done. Stage 3, where we applied regression and classification, and also annotation box were created. Stage 4, where we removed the overlapping, or you can say the post-processing part is done. So let me show you a live demo of how our model works. So first, this is same our folder of the detection. Here we go into COCO dataset. Here is our the FLIR dataset. We select any thermal validation dataset. We can select any image for which we have to do the annotation part. First, let us suppose we select this dataset. Just copy here, and then we go to our object data file folder. In the samples, we just remove all this, and then we just paste it over here. And then coming back to here, in the terminal, we have to run this code. After clicking on enter, it will use it basically runs on GPU. Here we are working on the CPU part, so it takes some time. So until then, let me describe you what, after implementing all these models, we merged over here. That is a detect.py model, where all the models are merged together, or the different blocks which we have used, and then all the results which are being produced here. So now it is using, as it's shown, it is using CPU here. So yeah, for the frame, it's shown here. There are 3 persons, 5 cars in the images. Also, this comes under the output folder of our video. Here we can see there are 5 cars and there are 2 persons over here. And then so the annotations come here with all the different 15 objects. Here there are only 2 objects are there, so it shows correctly. Also, we can show you the result precision, or you can say the evaluation matrix over here, which is basically this one. Example.png. This one, and this is our final results, which we are going to show. This is our precision, classification, regression, all the MAP which we discussed, like the mean, average, precision. So you can refer here for the results.
Now my other teammate, Parth, will be telling about the performance gains from the enhancement and our results and evaluation.
Just before I continue, this was the loss gains, my loss function my teammate was talking about. Moving on, let's take a closer look at how our enhancements improve detection performance, especially for tiny objects which are notoriously hard to detect in thermal imaging. So first, we evaluated our base model, EfficientDet D3, on the FLIR dataset and observed an initial MAP of 70.4%. With our Blockwise filtering, we improved that to 72.3% simply by discarding low information image blocks early in the pipeline. Then, by adding super resolution, adaptive anchor tuning, and context-aware detection layers, we reached a final accuracy of 77.3%. Most notably, person detection, which is often a small and a distant object in the FLIR scenes, it improved by nearly 3.8%, showing the clear benefit of targeted enhancement strategies. Moving on, another significant challenge in thermal detection is partial occlusion, which are basically objects being blocked by other elements such as vehicles or poles. So to address this, we introduced a multi-stage refinement mechanism where low-confidence detections from early layers were passed forward for reevaluation using deeper feature maps. So this approach allowed us to recover partially visible objects more reliably, especially in static scenes such as parked cars or people standing near traffic. As shown in the table, the MAP for fully visible objects is about 89.2%, while partially occluded objects reaches 55.4%. It is a slightly noticeable improvement over the baseline models, which typically perform worse on occluded objects. Still, we acknowledge that the dynamic occlusions, like moving people behind cars, they still remain a key limitation. Talking about results and evaluation, this slide it compares our method's performance with other state-of-the-art models on the FLIR dataset. So we evaluated 3 key classes: person, bike, and car, which are all critical for applications such as autonomous driving and surveillance. So compared to thermal det, our model shows improvement across categories, especially for bike and person, with overall accuracy increasing to 77.3%. Additionally, our ablation study, it confirms the effectiveness of each enhancement. You can see how each module incrementally improved the detection score, validating our design. So this is the sample input and output image for occluded objects, especially. You can see that it is successfully able to identify cars behind other cars. So to summarize, we proposed a modular and thermal-only pipeline that achieves state-of-the-art detection performance, particularly for tiny and occluded objects. Unlike GAN-based or transformer-heavy models, ours is a lightweight and suitable for real-time edge deployment, which is a big step towards practical use in fields such as UAV surveillance and ADAS. Looking ahead, our future work includes 5 key areas: temporal tracking, which using convolutional LSTM or transformers for better dynamic occlusion recovery; depth-aware occlusion modeling, which uses synthetic thermal depth data; model compression for Jetson, ARM, and Raspberry Pi platforms; cross-domain generalization by training on datasets like KAIST and DSIAC; developing a synthetic occlusion benchmark using game engines to test robustness in controlled settings. Finally, I'd like to highlight the broader relevance of our work. While we tested on the FLIR dataset, the applicability, it spans many domains, from perimeter security and nighttime surveillance to wildlife tracking and aerial search and rescue operations. Our pipeline, it provides a strong foundation for real-world thermal detection systems that are both accurate and deployable. And here we've included the key references for our paper that influenced and supported our work. So that concludes my section. Thank you.
So that was all for our presentation for the multi-stage framework for tiny and occluded objects in thermal images. Thank you.